now I'd like to introduce the next plenary speaker, Dr. Peter Mahaffy. He's a professor of chemistry and co-director of King's Center for Visualization in Science in Canada, which provides digital learning resources used by, well, over 250,000 students, educators, and the public from over more than 100 countries each year. Research and professional areas of the Dr. Peter Mahaffy includes chemistry education, system thinking in chemistry and education, visualization in science, public understanding of science, climate change science education, and organic chemistry, reaction mechanism, photochemistry, matrix, isolation, spectroscopy, and reactive intermediates. His professional service includes co-chair of Campus Alberta Quality Council, charter member of Organization for the Prohibition of Chemical Weapons, temporary working group on education and outreach. This organization received the Nobel Peace Prize in 2013. Editorial Advisory Board of Journal of Chemical Education. Past Chair, International Union of Pure and Applied Chemistry Committee on Chemistry Education and member of IUPAC Bureau. Editorial Advisory Board, Chemistry in Context. Charter member, International Council of Science, Committee on Freedom and Responsibility in the Conduct of Science. American Chemical Society Presidential Working Group on Climate Science. International Advisory Committee of various conferences, including chair of the Gordon Research Conference on Visualization in Science Education. He received numerous awards, including College Chemistry Canada Award in Chemical Education 2019, International Union of Pure and Applied Chemistry Committee on Chemistry Education Award for Distinguished Contribution to Chemistry Education 2012, American Chemical Society Committee on Environment and Industry Award for Incorporation of Sustainability into Chemistry Education 2012, section of the American Chemical Society James Fleck Norris Award for Outstanding Achievement in Teaching of Chemistry 2011, National Teaching Fellow Canada 2008, Alberta Centennial Medal 2005, Chemical Institute of Canada National Chemistry Education Award 2003, and Fellow of Chemical Institute of Canada since 1999. Please.
Can you hear me? Thank you for that very kind introduction. I have almost no time left for my presentation. It's a great honor and a privilege indeed to talk to you today about some ideas, some concepts that are perhaps a little bit new, systems thinking in chemistry education, and also the molecular basis of sustainability. And to be able to do so at the Mendeleev Congress here in St. Petersburg, and to do so in the middle of the International Year of the Periodic Table, for which Mendeleev played such an important role. One of the wonderful things about coming back to Russia for a conference is to meet old friends again and to make new friends. And I met an old friend who you will recognize, and I learned the vodka in St. Petersburg is a little different color than the vodka in Moscow and Tobolsk, where I've been before. But also making new friends. And I think, if I was counting right, this is the 118th new friend I've made at this conference, academician Oganessian. And what he's showing me here is Mendeleev's Chemical Principles, the 3rd edition. And so my talk is focused on chemistry education, and it's a real privilege to be able to do so in St. Petersburg, where Mendeleev did so much of his work. And so much of his work was focused, of course, also on chemistry education. So what I'd like to do to organize my presentation today is to start with a project of IUPAC. You've heard about IUPAC from Javier, a project on systems thinking in chemistry education. And from there to introduce the idea of the molecular basis of sustainability, which we would like to become a core outcome for chemistry education. And then introduce some tools to think about systems thinking, for educators to be able to use systems thinking. And the example I'll use will be a very familiar one after Javier's lecture. Finally, to talk about the next steps for systems thinking in chemistry education, which I'm abbreviating STICE. Chemists have learned well how to fractionate. You heard this also from Javier. In fact, Mendeleev traveled to Caucasus, to the beginnings of the oil industry, where we've learned a great deal how to take carbon atoms that are stored in the ground for geological time and to transform modern life through the combustion of fossil fuels. Chemists have learned how to do this very well. Can chemists also play a central role in solving the unintended transformations of all of those hydrocarbons? And I show you here the Keeling curve and going back to before the Industrial Revolution. We heard in a wonderful lecture yesterday from our colleague from Leiden that the oxygen-hydrogen bonds in water molecules typically are perhaps 4.5 billion years old. By contrast, if you look at carbon dioxide molecules, many of the carbon dioxide molecules in our atmosphere now have had their carbon-oxygen bonds formed during our lifetimes because of the scale at which we've been combusting hydrocarbons. And so understanding those cycles of carbon are very, very important. And to illustrate this, I'd like to show you a portion of a simulation we're working on at the Center for Visualization in Science, which I direct, kcvs.ca. And the focus of this simulation, which will be released publicly in about 2 weeks, is to help us understand how we can mitigate the greenhouse gases found in our atmosphere. So on the y-axis is the amount of carbon dioxide equivalents per year that human beings are producing. And we go back to the Industrial Revolution, and I've placed on that graph Mendeleev and the discovery of the periodic table. And you can see at the time of the discovery of the periodic table, the contribution of human activity to greenhouse gases, to changing the radiation balance of our planet, was very, very small. Nature had the capacity to assimilate those carbon dioxide molecules. But now, only 150 years later, as we celebrate the 150th anniversary of Mendeleev's periodic table, we're now producing almost 40 gigatons of carbon dioxide equivalents per year. And I'd like you to think with me for a moment as we look back on the wonderful celebration of the last 150 years. I'd like you to think with me about the future. So perhaps in St. Petersburg, in another 150 years, a group of chemists, none of us included, will be gathered to celebrate 300 years since Mendeleev's periodic table. But what will the concentration of greenhouse gas equivalents be in 300 years? This is the trajectory that we're on as human beings. And what role will chemists have to play in taking all of the little incremental steps? There is no silver bullet, but perhaps there is silver buckshot, if you understand that term. Many things that we can do, and you've heard some of them today from Javier and from our earlier speakers, to bring down the concentration of carbon dioxide and other greenhouse gases in our atmosphere. So chemists are very good at fractionating, but maybe have yet to really take on the task of the systems that have resulted from all of that combustion of fossil fuels. And now let's turn to chemistry education. I think chemistry educators are also very good. They're experts at fractionating. There's a quote by Joseph Bordogna, who was a former director of the National Science Foundation in the United States. And he talks about the importance of specialization in our world, in science education. We must have specialized knowledge. But in the process of teaching students all of that specialized knowledge, he uses the metaphor of fractionating. We continually fractionate knowledge, make it more and more specialized. And Bordogna asked the question, what other skills will be needed? And this was written in 1991 in the 21st century for students to be able to look to the future. And so my suggestion today is that one of the ways to move beyond fractionated knowledge in chemistry education is to use tools that have become important in other disciplines but are largely unknown in chemistry and chemistry education, and those are tools of systems thinking. So what do we mean by systems thinking? We use tools, strategies, and cognitive frameworks, our understanding of how students learn, to visualize interconnections and relationships among components of complex and dynamic systems. We examine how behavior of systems changes over time. And maybe, perhaps even most importantly, one of the things that happens when we look at systems is we see that systems have behavior that can emerge, that's greater than the sum of all of the parts. And so about a year and a half ago, we founded a project called the IUPAC Systems Thinking and Chemistry Education Project, which we call the STICE project for short. And it's with the motivation of applying systems thinking to chemistry education and to understanding how that can help the next generation address emerging global challenges. The project is co-chaired by Stephen Matlin from Imperial College in London, who's also been very involved with the International Organization for Chemical Sciences and Development. And we sat down and we asked about 24 leaders in chemistry education around the world whether they would join this project. And 24 people said yes. So here's a list of the IUPAC project team. And what I'd like to do today is to start and give you an idea of what we've been able to accomplish in a year and a half and what some of the next steps are. We began by going to the literature, and this work was published in Nature Reviews Chemistry a year ago, and develop a framework for systems thinking and chemistry education, learning from what other disciplines, particularly engineering, but the geosciences have done. And it's a framework for systems thinking and chemistry education. So we place learners, students, at the very beginning, the middle of that framework. And then we identified 3 subsystems, or 3 nodes, 3 elements of that framework. And the first is learner systems. So what are the general things that we know about learning, the theoretical frameworks of learning, learning progressions, the social context for learning, an important element in a framework for systems thinking and chemistry education. And secondly, how do those general understandings of learning apply to the very unique challenges of understanding chemistry, the world that of molecules and atoms that we can't see directly, full of models, full of mathematical relationships. And then finally, how might that system, the third node is the Earth and Societal Systems node, how might that apply to chemistry education as it relates to meeting social, societal, and environmental needs? One of the important outcomes has been a special issue of the Journal of Chemical Education, one of the 2 leading journals of chemistry education in the world. And we have a special issue which will be published in November or December of this year. And we thought we might have about 20 authors coming together to begin to understand the idea of systems thinking and chemistry education. And we received about 70 contributions to the paper, to the special issue. So look for this when it comes out. And the new incoming editor of the Journal of Chemical Education is on the project team, Tom Holm. So progress to date. let me just summarize what we've done and then pick a few things to talk about a little bit in more detail so that you have a concrete idea of what systems thinking in chemistry education might mean. We had to start by defining systems thinking and defining systems thinking in chemistry education. What's the purpose? What's the framework? We did a systematic review of systems thinking in other fields so that we could understand what we might learn from what other fields have done. And of course, one of the challenges in education of showing students the whole is complexity. So what pedagogical strategies do we have to deal with complexity? Skills and competencies for systems thinking. Tools and visualizations to help educators and students do systems thinking. And then how can we use systems thinking to address global challenges? And what learning frameworks can we use to develop this new area in chemistry education? We're also very interested in knowing how organizations that are responsible for education in different countries and regions, like accreditation agencies, standardized examinations, to bring them on board with this new idea of systems thinking in chemistry education. So I'm going to pick 3 of these and just talk a little bit more about progress in these areas. First of all, skills and competencies. And we've learned here from work that's been done in the earth sciences to take the different elements of systems thinking and to develop a little bit of a hierarchy, a pyramid, where at the bottom, what we'd like students to be able to do is to see the whole but analyze the system components. And then a series of activities, of skills and competencies that involve putting those together. And finally, of course, implementing, being able to apply that knowledge to things that matter. And this has been published in an early release of a paper from that special issue. The molecular basis of sustainability. This is work which has been done by the Earth and Societal Systems Group, or NODE, within the Systems Thinking Project. And that includes Stephen Matlin and myself, Tom Holm, the editor of the Journal of Chemical Education, and then 2 colleagues from the Green Chemistry Institute at the American Chemical Society. The molecular basis of sustainability is not a concept that we have invented, a new concept. It appeared very briefly in the literature. Paul Anastas and Julie Zimmerman at Yale University introduced the term, the molecular basis of sustainability, and they described it as saying many environmental issues have molecular considerations. We've now tried to take that important idea that was in the literature and develop it very fully in the concept of systems thinking. And so in a paper that was published in May of this year in Nature Sustainability, the ideas that we've put forward in that publication look like this. The flow of material and energy is integral to all aspects of society and the environment. What do chemists do? Our profession understands and controls matter through the activities of chemistry. And because of that, chemistry and chemistry education have a special responsibility to address the sustainability of Earth and societal systems. And so we define now the molecular basis of sustainability as the ways in which the material basis of society and economy underlie considerations of how present and future generations can live within the limits of the natural world. And the latter part of that definition you may recognize comes from the Brundtland Commission of Sustainability. And finally, the molecular basis of sustainability we think is a crucial but largely invisible aspect of sustainability agendas, and I'll give you a few examples of that. If you think about sustainability and sustainability agendas, perhaps the first things that will come to mind are some items that have appeared in the global press around the world. And one of them was earlier this spring, a major report from the United Nations showing that 1 million species face extinction. So the loss of biodiversity is one of the major sustainability challenges that we face. And perhaps the second thing that might come to mind is the data this goes back 800,000 years, of the carbon dioxide concentration in our atmosphere. And on May 18 of this year, that concentration at the Mauna Loa Observatory in Hawaii reached 415 parts per million. This is where we are in 2018. And the observation was made in headlines around the world that that level of carbon dioxide is more carbon dioxide in the atmosphere than at any other point since the evolution of human beings. The implications of that are staggering. And it's not only, of course, carbon dioxide, but a very important paper in Nature Climate Change identifies almost 470 traceable pathways for impacts on human health, water, food, economy, infrastructure, and security by multiple climate hazards, not all coming, of course, from carbon dioxide. And so what I'd like to do now in just a few minutes is to take two global sustainability agendas that much of the world has embraced, and to think about how this idea of the molecular basis of sustainability might contribute to that, might contribute to sustainability science. And the first is the one that you heard about from Javier, the UN Sustainable Development Goals. We'll come back to that. 170 targets require strategies based on consideration of systems in the flow of material and energy. You can't do that without chemistry, and I think, Javier, you showed that very, very nicely. But the second is the Planetary Boundaries Framework, first published in Nature in 2009, and then a very important follow-up in Science in 2019 by the Stockholm Institute of Resilience, the work of Johan Rockström and his group. And the Planetary Boundaries Framework is an attempt to quantify, to whatever extent is possible, the threat that we have to the sustainability of our planet from human activity. It identifies 9 Earth systems: climate change, ozone depletion, ocean acidification, and the colors are important. I can't point to them with the laser here, but if you look at the blue circle in the middle, and then there's a red circle following that, every one of these 9 Earth systems, there's an attempt to quantify a control variable that describes how far out we are proceeding on that Earth system on a journey away from sustainability. And so if you have a control variable that's within the blue circle, that's considered to be below the boundary, below the planetary boundary, a safe space for humanity. And when we come to the red circle, we're now moving from a zone of uncertainty into a region of high risk. And there are, you will notice, 2 of the Earth systems where we've exceeded, we're in the red. And one of them is loss of biodiversity. And the second is the nitrogen cycle, the nitrogen and phosphorus cycle that Javier was talking about. In the latest paper in 2015 in Science, 2 of those core systems have been described as core systems, because even though this is a system and every one of the Earth systems is related to the others, 2 of them on their own have the potential to drive Earth into a new state should we not do something about it. And that's climate change and loss of biosphere integrity. And so in our Nature Sustainability paper, we've identified a flow of ideas for education about the molecular basis of sustainability. First comes from recognizing the material basis of society as being important for sustainability. Then secondly, shaping the practice of chemistry by sustainability science. Reimagining, reorienting the way we do chemistry education to move from working with very isolated facts to seeing systems, and then to do so using systems thinking. So let me try to make that concrete so that you can imagine in perhaps a first-year chemistry course what this might look like. Maybe you'll have an answer for this after Javier's talk, which might be different than the answer you would have before his talk. What's the most important technological invention of the 20th century? And many people say, maybe the computer chip. The case has been made that the Haber-Bosch process is the most important technological invention of the 20th century for the reasons that Javier made. You might think that we got together and coordinated our presentations here. But that case has been made by a Canadian, Vaclav Smil, who says that without the Haber-Bosch process, perhaps 40% or 50% of the world's population would not be here. An incredibly important contribution of chemistry to the survival of humanity. But yet that very important process that Javier talked about might also be thought of as a failure of systems thinking. And I say that because if you think of 100 nitrogen atoms produced in that Haber-Bosch process in the factory in the form of ammonia, and you look at following those nitrogen atoms all the way through the chain until you eat a hamburger, you find that 96 of those nitrogen atoms are lost. And if you're a vegetarian, the situation is only a little bit better. 86 of them are lost. So we have failed, as we have this wonderful technology to give us nitrogen atoms for our bodies, we failed to do that in a way that considers this as a system. But this is also, I think, a failure of systems thinking in chemistry education. You might imagine, and maybe your situation is different in Russia, but in North America, every first-year chemistry text in university has the Haber-Bosch reaction. And it looks something like this. There will be a reaction shown in a chapter on equilibrium, even though, as you've heard, it's mainly kinetics and catalysis that's important. And there will usually be a little sidebar that says, Fritz Haber was a German chemist. He received the Nobel Prize in 1918 for his invention of the Haber-Bosch process to make ammonia from nitrogen and hydrogen. He called it making bread from air. And then you look at how a textbook develops this idea, and usually it's limited to equilibrium calculations. Can you change the concentration of nitrogen? What happens to the amount of ammonia? And so on. No connection is usually made between the Haber-Bosch process and the survival of 50% of our planet on the one hand, or the threat to our planetary boundary from the fact that we've fixed too much nitrogen on the other hand. So a failure of systems thinking in chemistry education. So what might we do about that in chemistry education? And think whether there are some ways in which, in your own teaching, if you're an educator, you might be able to do this. And the analogy I like to use is if you have a cell phone, you can zoom out. So you can take this theater where we are and you can go to Google Maps and you can zoom out, and pretty soon you can see this complex and this university in the context of Russia and in the context of our planet. We can look at the whole, and then we can zoom in and look at part of it. So we've developed some tools on the project to visualize the interconnections among system components. And we call these systems-oriented concept map extensions. Okay? I'm sorry if we had a translator here, the translator would be pulling her hair out. It's perhaps difficult to find the right language for this, but it's a concept map. And it's showing the relationships, the interconnections among system components. And we picked that name because it has a nice acronym, SOCME. So we've developed SOCMEs to visualize these interconnections. And these ones that I'm going to show you have been drawn by Tom Holm, a project member. And the idea is to be able to zoom out to help students see the whole, but then to be able to take a part of it after they see the whole and define some boundaries, which then become the focus of study for a particular unit. And this can help us see emergent behavior change over time and cause-effect relationships. So let me illustrate with the Haber-Bosch process. So this is what has been done in the chemistry textbook that I was taught chemistry from. There's a simple reaction, N2 plus H2 gives ammonia, some calculations based on that, and that's the extent of what students learn. So with a system-oriented concept map extension, one can say, okay, how could we see that by zooming out? What are the other dimensions to that? And one of them, of course, are the reaction conditions that are needed to make ammonia. It requires a catalyst, it requires temperature above 350 degrees to form ammonia at a practical rate. And so now we've expanded the system to look at the reaction conditions. And there are topics here now that could be considered in another section of the course that deals with equilibrium and kinetics. What about the chemical inputs? You've heard about that again from Javier. So the hydrogen and the nitrogen are generally produced unsustainably now. Work done by a colleague at Dalhousie University in Canada. The hydrogen starts from methane in the steam reforming process. It comes from fossil fuels. And to produce 1 kilo of ammonia requires the consumption of 3 kilos of methane and produces 3.5 kilos of carbon dioxide. And then we could expand the system to look at the energy inputs. And as you've heard from Javier, 80% of the cost of ammonia is the cost of natural gas. This chemical reaction, this single chemical reaction, uses about 2% of the total annual energy supply. And that has real implications for society. So if we look at some data which shows natural gas and oil, and this is the cost of those commodities, nitrogen fertilizers are the single largest operating cost for many farmers around the world. And we had spikes in nitrogen fertilizer costs in 2008 and 2011 because of the cost of natural gas. And the implications of those spikes can actually be traced fairly significantly to some global events that relate to what happens when populations now have a scarcity of food. So this Haber-Bosch process, depending on methane as an input, very, very real implications for one of those UN Sustainable Development Goals. And then, of course, that ammonia is used through the cycle of the Oswald process to produce nitric acid and ammonium nitrate. And we do that for intended uses. We do that so that we can produce fertilizers. And 80% of the ammonia that's produced goes into fertilizers, largely in the form of ammonia, urea, and ammonium nitrate. And then 20% is used for all sorts of other things, from pharmaceuticals to materials, including materials to capture carbon dioxide from the air with the form of amines. But then not everything from ammonia and the ammonium nitrate leads to intended consequences. We also have unintended consequences. And those unintended consequences include health effects of reactive nitrogen, too much fixed nitrogen, but also, of course, eutrophication. And you have here what happens when phytoplankton bloom as a result of far too much reactive nitrogen going into the ocean off the coast of Florida. So let me put this together now. Here's the system, starting with what we usually teach, and zooming out and looking at the other elements to that system that we'd like to help students see if we think about this as in the context of a system. And then, of course, we can zoom in again and look at one part of it, but at least students now see the whole first. And so if we have the different subsystems shown here, along with the intended and unintended consequences, now it's possible for us to see some of the things that emerge, the emergent phenomena, and I will end with this. Let's take that system of the Haber-Bosch process and think about the implications of that for these two sustainability agendas, for the planetary boundaries framework and for the UN Sustainable Development Goals. So we look first at the planetary boundaries. This is one of the two Earth systems which is in the red, which has far exceeded the planetary boundary that's been set. The planetary boundary, which is the amount of industrial and intentional biological fixation of nitrogen, has been set at 62 teragrams of nitrogen per year, and we're almost 3 times that, 2.5 times that, 150 teragrams of nitrogen per year. And so that boundary has been exceeded, and the unintended consequences of that are very significant. But if we think of this as a system, of course, the planetary boundaries framework is a system in itself, and the amount of reactive nitrogen does not only affect that planetary boundary, but one can think about the implications of that for stratospheric ozone depletion, because nitrous oxide is one of the ozone depleters in the stratosphere. The implications for climate change. Nitrous oxide, again, is a potent greenhouse gas, contributing perhaps about a quarter of the total change in radiative forcing of carbon dioxide since the Industrial Revolution. It's related to biosphere integrity. It's related to land use changes. It's related to fresh water availability. And so when we think about this as a system, this one chemical reaction has very, very significant implications for the planetary boundaries sustainability framework. And then let's look at what that might look like if we were to look at the biogeochemical flow of nitrogen and the UN Sustainable Development Goals. Well, of course, the most obvious one is that ammonia feeds people, produces plants that feeds people, and so achieving zero hunger, incredibly important that we find better ways to produce ammonia. That's related to poverty, good health, well-being. Hungry people are not well, and they live in poverty. But of course, one of the other major uses in the last century of fixed nitrogen was the production of explosives, and probably 100 million people in the last century died as a result of nitrogen explosives. And for both of those purposes, fertilizers and explosives, we need energy, as we've discussed, with real implications for the UN Sustainable Goal number 7, and consequences of that production of ammonia, largely nitrous oxide production, which is done by microorganisms on legumes and other plants. They're able to take nitrogen, and in the process of nitrification and denitrification, they make laughing gas, nitrous oxide. Overproduction, implications for responsible consumption and production, life on land, life below the water, and clean water and sanitation. So this one chemical reaction, which we usually focus on as a very narrow reaction, major implications for the UN Sustainable Development Goals. So let me finish by just telling you what's next for the Systems Thinking project. We had a project meeting at the IUPAC Congress in Paris a few months ago, and future directions for the project have been set out by several colleagues on the project, Mary Kay Orgill, Felix Ho, and Alison Flynn. And it's very difficult to change the way educators teach and to change curriculum. The planet is accelerating these parameters. The great acceleration is going up exponentially, and educational systems change at the rate of glaciers moving. It's very difficult. It's very, very slow. And so we've identified the things that are needed if systems thinking in chemistry education is to take hold. And one of them, of course, is we have to tie this, ground this in learning theories, so there's evidence that systems thinking actually can work in the teaching of students. We need to connect to curriculum and program standards. We need to define learning outcomes for students based on systems thinking, activities and assessments aligned with learning outcomes. If you have a new approach and then the final exam is exactly the same as it used to be for 30 years, then of course students very quickly will learn this other material is not really very important. Training opportunities, and we'd like to create a virtual user community. And of course, we need to do some chemistry education research to provide the evidence for a pedagogical approach that can actually make a difference in student learning. And this work, including examining who might benefit most from a systems thinking in chemistry education approach, is forthcoming in one of the issues of the special issue of the journal on future directions for systems thinking in chemistry education. So what I've tried to do today is to give you an introduction to systems thinking in chemistry education, hopefully asking you to think about the chemistry education that you were taught with, or perhaps that you currently teach, and to examine whether there are ways in which systems thinking will allow you to help your students see the whole, to understand how relevant the chemistry they're learning is to emerging global challenges. I hope I've convinced you to think a little bit more about the molecular basis of sustainability. It would be wonderful if students coming in to university, coming into secondary school, would see that when they go home and talk to their parents, they say, I learned how important chemistry is to contribute to sustainability on our planet. I've given you some examples of some tools that can be used to do that, and then an idea of where the project's going. And if any of you are interested in being involved in the project, I'd really like to ask you to contact me. And I'd like you to think about the time frame. So we celebrate the 150th anniversary of the periodic table. We don't have 150 years. We don't have until St. Petersburg 300 years after Mendeleev to tackle these sustainability challenges. We have maybe 30 years, maybe 20 years, and we have to make progress, and chemistry has to be a central science contributing to that. We won't do that as a profession of chemistry without changing the way we educate. So let me acknowledge the Congress Organizing Committee. Thank you for the invitation to present here, but thank you even more for featuring chemistry education and sustainability on a plenary forum for this Congress. I think it's incredibly important that that was done. I'd like to thank the members of the STICE Project Steering Group. This is at our group meeting a year ago in Australia. And Stephen Matlin is my co-chair, and IOCD has become involved in supporting the project. Tom Holm, whose work I featured today, and then Felix Ho and Mary Kay Orgel and Allison Flynn have done the work on future directions. And the American Chemical Society Green Chemistry Institute, Jenny McKellar and her colleague David Constable have made seminal contributions to the project. Spasiba.